Imagine cruising at 35,000 feet over the Pacific, the flight smooth, the cabin calm. Suddenly, the pilots lose GPS, their digital map goes dark. How would they navigate the invisible highways of the sky without their trusted guide? Our reliance on GPS is both a marvel and a vulnerability. GPS signals are faint, easily blocked or jammed, and in conflict zones even spoofed, turning a lifeline into a liability. For military missions or commercial flights, losing GPS isn't just inconvenient, it's a critical failure. But before GPS, humanity had already solved this problem. We built a system that senses its own movement, an Inertial Navigation System, or INS. The INS is the silent guardian aboard aircraft, missiles, submarines, and spacecraft, taking over when satellite signals vanish. Think of it like walking across a room with your eyes closed. You sense your steps and direction. An INS does this, but with incredible precision. It's a self-contained box of sensors tracking every push, pull, and twist, needing no outside help. This is the magic of inertial guidance, navigating from the inside out. So, how does a machine know where it is without looking outside? The INS is a dead reckoning system. Start at a known point, then track every movement, speed, direction, and time. It gets its starting position, often from GPS, then takes over, relying on internal sensors to feel every change. Submarines deep underwater, missiles in flight, jets in jammed airspace, all depend on INS when GPS is unavailable. The INS isn't just a backup, it's the primary navigator in these scenarios, providing a continuous, unjammable stream of data. The secret? Two types of sensors: accelerometers, which measure linear motion, and gyroscopes, which track rotation. These sensors are the system's eyes and ears, perceiving the world through forces and motion. 3 accelerometers and 3 gyroscopes, each aligned to a different axis, capture every movement in 3D space. Together, they create a complete picture of the vehicle's journey, moment by moment. This self-contained awareness is what makes INS so powerful. It's how machines feel their way, even in total darkness. Let's break down how these sensors work. Accelerometers measure acceleration, how quickly speed changes, using tiny structures that bend or vibrate. 3 accelerometers track movement in all directions, forward, back, side to side, up, down. Gyroscopes, on the other hand, sense rotation. Imagine a spinning top that resists being tipped. Gyros use this principle to maintain orientation. 3 gyroscopes track pitch, roll, and yaw, telling the system exactly how it's oriented. The INS's computer combines this data, calculating velocity and position by integrating acceleration and adjusting for orientation. This high-speed math happens thousands of times per second, keeping track of every move. The technology isn't new. Apollo missions to the moon relied on INS to guide astronauts safely, even when computers overloaded. INS made it possible for Neil Armstrong to land the Eagle on the moon, proving the power of navigating by feeling motion. Today, the same principles guide everything from jets to submarines. It's a dance of physics and precision, at the heart of modern exploration. But INS has a weakness: drift. Tiny measurement errors add up over time, causing the calculated position to slowly wander from reality. It's like walking with your eyes closed. A small mistake at the start becomes a big miss at the end. Manufacturing imperfections, temperature changes, even gravity variations can introduce errors. For short trips, drift is minor. But for long journeys, like submarines under ice or spacecraft in deep space, it can become a huge problem. The solution? Combine INS with GPS. GPS provides accurate long-term fixes. INS fills in the gaps when GPS is lost. Together they create a hybrid system. GPS corrects INS drift. INS keeps you on track when GPS drops out. This partnership gives us robust, reliable navigation, immune to jamming, precise over time. It's the best of both worlds, making modern travel safe and accurate. Think of the INS as a machine's inner ear, always on, sensing motion and orientation, even in total darkness. It's what lets missiles hit targets when GPS is jammed, jets fly through storms, and submarines navigate under polar ice. Today's INS uses advanced sensors, ring laser gyros, fiber optic gyros, even MEMS chips, making them smaller, cheaper, and more reliable. INS technology is now in everything from drones to smartphones, giving even tiny devices a sense of motion. So next time you see that airplane icon on your flight map, remember, GPS draws the map, but INS feels the journey. Even if the sky goes dark, the INS keeps us from ever being truly lost. Sometimes, the most important thing is to know ourselves, so we can always find our way.